Welcome to this beginner-friendly guide on C-sharp IEnumerator and yield return in Unity 3D, essential tools for game development. These powerful features are fundamental for creating dynamic and responsive game mechanics, allowing for efficient management of time-dependent operations within your projects. We'll explore how these concepts enable coroutines, which are special methods that allow you to spread tasks across multiple frames. This technique is crucial for preventing frame rate drops, ensuring your game runs smoothly, and significantly improving overall performance, especially in complex scenarios. This video is meticulously tailored for beginner programmers and Unity developers, providing clear, step-by-step demonstrations. We will walk through practical examples in both Visual Studio for understanding the core C-sharp concepts and the Unity engine to see them applied in a game development context. Let's begin by understanding what coroutines are. Fundamentally, a coroutine is a method that possesses the unique ability to suspend its execution at a certain point, pause for a specified duration or condition, and then resume later from precisely where it left off, maintaining its state. Unlike regular methods that execute entirely from start to finish before returning control to the caller, coroutines offer a sophisticated and flexible way to manage time-dependent operations more efficiently. This distinction is vital for non-blocking operations in game development. In Unity, coroutines are incredibly useful and versatile for a wide array of tasks. These include creating smooth animations, implementing gradual fade-out effects for UI elements or objects, or waiting for asynchronous operations such as HTTP transfers to fetch data from a server or asset loading to complete without freezing the game. It's crucial to remember a key distinction. Coroutines are not threads. They execute entirely on the main thread of your application, meaning they don't introduce the complexities, overhead, and potential pitfalls associated with multi-threading, such as race conditions or deadlocks. They simply manage execution flow on a single thread. Next, let's delve into the IEnumerator interface. This fundamental interface defines a standard set of methods for iterating over a non-generic collection of objects. It is a core component of the .NET framework and is found within the System Collections namespace, providing a powerful mechanism for sequential access to elements. Key members of the IEnumerator interface include moveNext, which is responsible for advancing the enumerator to the next element in the collection. It returns true if the enumerator was successfully advanced to the next element, or false if the end of the collection has been reached, indicating no more elements to iterate over. The current property, another vital member, gets the element in the collection at the enumerator's current position. Additionally, the reset method sets the enumerator to its initial position, which is before the first element in the collection, though it's rarely used in typical Unity coroutine scenarios. Behind the scenes, many familiar constructs in C#, such as the convenient for each loops, rely heavily on both the IEnumerable and IEnumerator interfaces to function. These interfaces provide the underlying mechanism that allows you to easily iterate through collections without needing to manage indices manually. Now, let's explore the yield return statement. This powerful statement is exclusively used within iterator blocks, which are special methods that return either IEnumerator or IEnumerable. Its primary purpose is to provide the next value in an iteration sequence, allowing for deferred execution and state preservation. When a yield return statement is encountered during execution, it immediately pauses the method's execution at that precise point and returns the specified value to the caller. Crucially, the next time a value is requested from the iterator, execution seamlessly resumes from that exact paused point, with all local variable states perfectly preserved. Additionally, the yield break statement serves a distinct purpose. It is used to signal the explicit end of an iteration. When encountered, it terminates the sequence prematurely, preventing any further elements from being yielded, effectively stopping the iteration process before it naturally completes. Let's see this in action with a practical Visual Studio demonstration. We'll create a simple C# console application to illustrate how yield return works by generating a sequence of even numbers, providing a clear and concise example of its functionality. Here's the code for our example. We define a method named produceEvenNumbers, which utilizes a standard for loop. Inside this loop, The yield return statement is strategically placed to generate and return even numbers sequentially, up to a specified limit, pausing execution with each number produced. The main method then orchestrates the consumption of these numbers. It iterates through the sequence generated by produce even numbers using a convenient for each loop, printing each even number to the console. This demonstrates how the yielded values are received and processed. By setting a breakpoint inside the for loop within our produce even numbers method and carefully stepping through the code using the debugger, we can vividly observe how yield return effectively pauses execution, returns a value to the caller, and then awaits the next request to resume. This debugging process clearly demonstrates how the for each loop implicitly interacts with the iterator. It repeatedly calls the moveNext method of the underlying IEnumerator to advance to the next element and then accesses the current property to retrieve each subsequent value, showcasing the elegant mechanism at play. Now, let's transition our focus to a Unity 3D engine demonstration to see coroutines in a game development context. We'll start by creating a brand new Unity project and then add a simple cube primitive to the scene, which will serve as our visual subject for the coroutine. Next, we'll create a new C# script, which we will name coroutine example. Once created, we will attach this script directly to our cube object in the scene. This attachment links the script's logic to the cube, allowing it to control the cube's behavior. Inside this newly created script, we'll implement a coroutine that will dynamically change the color of the cube every second. This practical application will vividly showcase how coroutines can be used to create time-based visual effects and manage sequential actions within your Unity games. The wait for seconds statement is a key component here. It instructs the coroutine to pause its execution for a specified duration in seconds. Crucially, it does this without blocking the main thread, ensuring that your game remains responsive and the frame rate stays smooth during the pause. We initiate this coroutine using the start coroutine method, typically called within the start method of our monobehavior script. This ensures that the coroutine begins its execution as soon as the game object it's attached to is enabled and active in the scene, setting our color changing process in motion. When we run the Unity scene, you'll observe the cube's color dynamically changing every single second. This continuous and smooth color transition is a direct and visible result of our coroutine diligently working in the background, demonstrating its effectiveness in managing timed events. Let's now review some helpful tips and best practices that will enable you to effectively and efficiently use yield return statements and coroutines in your Unity projects, ensuring robust and performant code. Common yield return statements are fundamental for controlling coroutine flow. These include yield return null, which pauses the coroutine until the very next frame, and yield return new wait for seconds, which introduces a specific, precise delay for a given number of seconds. You can also use yield return new wait for end of frame to ensure the coroutine waits until after all rendering has completed for the current frame. Alternatively, yield return new wait for fixed update is used to synchronize with the next fixed frame rate update, which is essential for physics-related operations. Furthermore, yield return start coroutine is a powerful construct that allows you to chain coroutines. This means one coroutine can pause its own execution and wait for another specified coroutine to fully complete before it resumes its own operations, enabling complex sequential behaviors. Coroutines are ideally suited for a variety of common game development tasks. These include creating fluid animations, implementing precise timers and cooldowns for abilities, orchestrating sequences of actions with specific delays, and efficiently loading assets asynchronously without interrupting gameplay. Important considerations when working with coroutines include remembering that they execute on the main thread. Therefore, it is crucial to avoid placing long-running, blocking operations within a coroutine, as this will still cause your game to freeze or experience significant frame rate drops. Always use stop coroutine to explicitly stop a coroutine when it's no longer needed or when its task is complete. Failing to do so can lead to unnecessary processing, memory leaks, or unexpected behavior, especially if the game object is destroyed but the coroutine continues to run. While coroutines are powerful, it's good to be aware of modern alternatives. C# offers the async/await pattern for asynchronous programming, which can often simplify certain tasks, especially when dealing with I/O bound operations or external services, providing a more structured approach to asynchronous code. For truly heavy, CPU bound tasks, you might consider utilizing threads to offload work from the main thread. However, exercise extreme caution, as the Unity API is not thread safe, and any interactions with Unity objects or functions must be marshaled back to the main thread, adding significant complexity. Unity's job system, combined with the Burst compiler and entity component system, is specifically designed for performing highly optimized, parallel computations on multiple CPU cores. This system offers unparalleled performance for complex, data-oriented operations, making it ideal for demanding game logic. Additionally, Awaitable is a custom Unity type that provides another robust option for asynchronous programming within the Unity ecosystem. It offers a more Unity-centric approach to async operations, often integrating more seamlessly with Unity's update loop and object lifecycle than raw C# task-s. These various asynchronous functions and systems in Unity collectively allow you to process complex logic without blocking the main thread. This means that heavy or long-running tasks can execute efficiently in the background, ensuring that the game continues to run smoothly and remains responsive to player input. In conclusion, we've thoroughly covered the key concepts of C#, IEnumerator, and yield return, demonstrating their fundamental power and versatility in both a standalone Visual Studio environment and within the dynamic context of the Unity engine. We've seen how they enable controlled, paused execution. Coroutines are incredibly useful and an indispensable tool for creating time-based and multi-frame behaviors in your Unity projects. They are essential for making your games more dynamic, responsive, and performant, allowing for complex sequences of actions to unfold smoothly over time without hitches. We strongly encourage you to experiment with these powerful concepts, integrate them into your own projects, and explore their diverse use cases. Mastering IEnumerator and yield return will significantly enhance your game development skills and open up new possibilities for creating engaging and efficient game experiences.